right, seeing that it's 12:01, let's go ahead and get started. Hello, everyone. Thank you for sharing your lunch hour with us. My name is Abby Wakely, Socora's Communications Director, and I will be facilitating and moderating the webinar. Welcome to the first of 4 webinars on how to use sea level data in the classroom. Each webinar is being recorded and will explore the different sections of a curriculum developed for middle school students. This curriculum provides students the opportunity to actively investigate climate change and the phenomenon of sea level rise. Before getting started, I wanted to quickly introduce Socorra. Socorra is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System. This is a quick snapshot of the technology we support to accomplish our mission. Our mission is to sustain and promote observations that help keep you safe. Here is Socorra by the numbers. We are growing every year. All right, let's get to the reason you are all here, the webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenter or technical questions for me in the bottom right-hand chat box. I will respond to them directly or post the questions to our presenters after their presentation if there is time. We're recording this webinar today and we'll be posting the recording on the Socorra website. Webinar 1, Causes of Sea Level Rise, will explore what effect, if any, do melting sea ice and land ice have on sea level rise. I am excited to welcome Jayma Koval and Dr. Alex Roble from the Georgia Institute of Technology. Jayma Koval is a research associate at the Educational Innovations Group at the Center for Education, Integrated Science, Mathematics, and Computer at Georgia Institute of Technology. Jayma received her BS in Meteorology from Pennsylvania State University, a MS in Earth Science Adolescence Education from Long Island University, and an Educational Specialist degree in Science Teaching and Learning from Georgia State University. At Georgia Tech, Jayma focuses on educational research in the K-12 setting, curriculum development, and teacher learning. Prior to her career at Georgia Tech, she taught middle school earth, life, and physical science for over 10 years in both Georgia and New York. Alex Roble is originally from Miami, where he grew up at 4 feet above sea level. He received his BS in Earth Sciences and Physics at Duke University before going on to pursue a PhD in Earth and Planetary Sciences at Harvard, where his dissertation focused on the theory of modeling of ice sheet melt. Alex then worked at Caltech and the University of Chicago as a NOAA Climate and Global Change postdoctoral fellow. Since 2018, Alex has been a faculty member in the School of Earth and Atmospheric Sciences at Georgia Tech as the head of the Ice and Climate Research Group. His work is focused on understanding the causes of ice sheet change and developing conceptual mathematical and tools to predict future changes. All right, so I am going to stop sharing my screen and then pass the controls over to Alex and Jayma, which everybody should see on the video. And you guys can go ahead, I believe, and unmute yourself. Just give me 1 second. All right, I'm promoting you to presenter, and I can hear you. Good.
Great.
All right, and I see your screen. Perfect.
Okay, well, thanks for introducing us, and I'll let Jayma get started.
Okay, so today's agenda for our first webinar, we're going to give you a brief overview of the entire curriculum, what it looks like, and specifically today we're going to talk about sea level rise science and an overview of the activity, what effect, if any, do melting sea ice and land ice have on sea level rise. So to give you an overview of the curriculum, we've created a phenomenon-based module that transports students to the Savannah-Tybee Island region to better understand how coastal flooding, tides, sea level rise, and climate change are impacting these communities. The curriculum is aligned with middle school earth science and statistics and probability standards and is supported by the Smart Sea Level Sensors Project, a unique partnership between Chatham County emergency management officials, City of Savannah officials, Georgia Tech faculty, and additional partners who are working together to install a network of internet-enabled sea level sensors across Chatham County. Implementing this entire curriculum would take approximately 1 to 2 weeks, and it follows the 5E model of instruction. Over the next few webinars, we will highlight activities from the curriculum and discuss the science content in some depth. One important point that we want to highlight is that although the curriculum is focused on the Savannah region, it can be adapted for any coastal location. And we also recognize that depending on classroom constraints, teachers may only want to implement a handful of activities rather than the entire module. Hopefully, these webinars will be a useful resource for aiding with classroom implementation. Like any curriculum, this one is open to revision, and we'd love to hear your feedback from implementation. So let's get started.
So I'm going to sort of give everyone a bit of an overview of sort of a lot of the basic ideas of sea level science, and sort of how we think about this question of like, what is sea level, what does it mean, and why does it change over time? So when we think about sea level, we might think about a picture that looks like this. You're at the beach, you're sort of looking out on the water, and sort of simplest answer to that question of what is sea level is sort of it's the level at which the surface of the ocean lies. But it's actually a bit more complicated than that, and that's because the ocean sits on the surface of the Earth, which is bumpy and rough, and has changes in gravity, the strength of gravity over the surface of the Earth. So people in the field of sea level science, which I'm a part of, think about sea level a bit more like this. So here's sort of a simplified schematic of how we think about the idea of sea level. So the blue line here is the sea surface. That's on the previous slide. When you're looking at the surface of the ocean, what you might see as the sea surface. And that sea surface sits on top of the crust of the Earth, which undulates and changes over space, and gets deeper in the ocean basins, and might vary along the surface of the Earth in various ways. And so the way that we think about sea level is about this concept of relative sea level. So you can see here on the left side of this diagram, we've put a green arrow which shows the difference between the crust of the Earth, so that's like the ocean floor, the sea floor, and the sea surface. And that difference, which is basically the thickness of the water column in the ocean, is what we refer to as relative sea level. And the reason why that relative sea level concept is important is because it depends on both how gravity spreads water over the surface of the Earth, and also where the position of the seafloor is. So what this helps us do is take into account other things that might affect sea level, or the sea level that you see, let's say when you're at the beach, other than just how much water is in the ocean. And so what I want to sort of have you take away from this sort of just introductory slide and this notion of relative sea level is that above all, sea level is local, right? So there is an idea of the global mean sea level, which is that if we took a measurement of the position of the surface of the ocean at every point on the Earth, and then we took an average over the global ocean, we would have something called global mean sea level. But as far as what people experience in their day-to-day lives, it's really the local sea level. And local sea level can actually have quite large departures from this idea of global mean sea level. And a lot of what folks in the research community are now engaged in doing is trying to understand what causes those variations in local and global mean sea level. So here is a plot from the last IPCC assessment report from a few years ago, which shows sea level over the last, so this is global mean sea level again. So this is the average sea level over the surface of the Earth, taken from a baseline of what it was before sort of the industrial era. Through using a combination of proxy measurements, so these are sort of geological measurements of sea level in the past before we were measuring it with tide gauges, combination of proxy measurements, a combination of tide gauges, explicitly measuring sea level, and then in the more recent era, that is combined together with very precise satellite measurements of sea level. And a little bit later in this webinar, I'll talk a bit about sort of the different technologies that are used to measure sea level. So this is sort of the summary plot that you will often see to talk about the idea of global mean sea level rise. So what you can see is that since sometime in the late 18th century or early 19th century, sea level has been rising at a rate that, depending on what exactly you're measuring or which time period you're measuring in, has varied anywhere in between 1 and 3 millimeters per year on this global average. And so the question is, of course, then why does sea level change? And this is where it's really important and critical to go back to this concept of local sea level. Because if we look at sort of all of the different processes on the surface of the Earth that contribute to setting both local and global sea level, you can see that it's actually a sort of a more complicated problem than how much water is in the ocean. So just to point out a few processes on this schematic figure, the two that you might think about more often when you think about sea level rise are glaciers, which is sort of the terminology that we use to refer to the localized ice bodies that are typically found in mountainous areas on continents, and then ice sheets and ice shelves, which really just encompasses the Greenland ice sheet and the Antarctic ice sheet. And when those melt, they can put water into the ocean, and then global mean sea level rises as a result of that. But there are more processes that are playing a role here. That is, the atmosphere and ocean, they interact, and water moves in and out of the ocean and falls as precipitation. Also, the atmosphere exerts pressure on the surface of the ocean, which can depress the ocean on timescales of hours to decades. There can be these variations in atmospheric pressure, persistent variations in atmospheric pressure that cause changes in local sea level. And then also properties of the ocean. So actually the largest current source of sea level rise, as we'll see on the next slide, or on one of the next slides, is the thermal expansion, or the expansion of ocean water. So ocean water is becoming slightly less dense as it becomes warmer. And that is the largest current source of sea level rise. So all of these different processes contribute to setting this sea level rise that I showed on the last slide, but also go to setting variations in local sea level as well. And so you can see this again from the last IPCC assessment report. You can see this sea level rise broken down. So this is a table showing the different sources of sea level rise, the different significant sources of sea level rise, broken down in terms of millimeters per year of sea level rise. So the observed and total of these contributions is about 3 millimeters per year. And this is broken down at least over the last 20 or so years. This has been broken down about 1/3 thermal expansion, another third or so of, and then 2/3 of glaciers on continents and the ice sheets of Greenland, on Greenland and Antarctica. And then also a small portion due to changes in water storage on land as well. Okay, so focusing in on glacier melt, which is my area of expertise, glacier melt is really the largest unknown in future sea level rise and thinking about future sea level rise. So here's a map that just shows kind of where all the ice is on the surface of the Earth, and the white areas on this map. And the reason why you can see that this glacier melt in the future is such a large unknown is that even though we've only seen order of maybe some 10 centimeters of sea level rise from glacier melt over the last 100 or so years. The rest of the mountain glaciers in the world comprise another 40 centimeters of sea level rise, but then there's another 60 plus meters of sea level held within the Antarctic and Greenland ice sheet. And although we don't think that it's feasible that a significant fraction of that will necessarily melt over the next several centuries, a lot of what current research is focused on is trying to understand what controls how fast these Greenland and Antarctic ice sheets will melt in the future, because they are such large potential sources of sea level rise. The other thing to keep in mind here is that, and I was sort of referencing this before, is that the ocean and sea level doesn't move up and down like a bathtub, which is to say that when you take a piece of ice on land and you melt it and put the water into the ocean, the average level of the ocean does not go up and down or down the same everywhere. And this is because of really two processes. One is that ice sheets are so large that they exert a gravitational attraction on the ocean, which means that the surface, or sort of the sea level right near ice sheets, is slightly sloped up as you go towards the ice sheet. That means when you melt the ice sheet and put that water into the ocean, that water is distributed over the entire surface of the global ocean, but the gravitational attraction, or the decreased gravitational attraction of that ice sheet, causes sea level to actually drop right near the ice sheet. So if you actually look at measurements, satellite measurements of sea level change over recent years, what you can see is that sea level has actually dropped near the south coast of Greenland, and also dropped in some parts of Alaska nearby glaciers. And this is because of that decreasing gravitational attraction. And then the other effect is what's called glacial rebound, which is basically as you add more water to the oceans, the ocean floor depresses a little bit underneath the weight of that water. So when we make predictions about future sea level rise, we need to make predictions both of global mean sea level, but then again also the changes in local sea level that are occurring in different places, which include all of these different effects. And so you can see here is an example of how sea level would change if you melted a layer of ice off of the Greenland ice sheet. And red indicates sea level dropping and blue indicates sea level rising. So over most of the Earth, sea level would indeed rise, but in places close to the Greenland ice sheet where ice is being lost, sea level will drop. And that includes sort of getting into the northeastern part of the US and parts of Atlantic Canada as well. Okay, so a few final slides here to just sort of talk about basic terminology that it particularly is important for thinking about the curriculum that James is going to review here in a few slides, which is that there's sort of different terminology to refer to different forms of ice on the surface of the Earth. So at the North Pole and near Antarctica, in the South Pole, it gets cold enough in the winter that the surface of the ocean can be frozen by cold atmospheric temperatures. And when that occurs, you get the formation of what's called sea ice. So this sea ice is forming in situ at the surface of the ocean, and it's floating in ocean water, which means that it is displacing water and it is not contributing at all to sea level rise. So when you hear about the melting of sea ice in the Arctic, for example, that is in no way connected to sea level rise. Now, glaciers and ice sheets are different because they sit on top of land, which means that the weight of the ice is not being displaced by ocean water. So when glaciers and ice sheets melt, the meltwater from those ice sheets finds its way to the ocean, and then it can contribute to sea level rise. Ice shelves are sort of somewhere in between, where ice shelves are basically as ice from glaciers and ice sheets flows towards the ocean, it can become thin enough that it can float on top of the ocean. And where it's floating on top of the ocean, it is also displacing an equal amount of water to its volume, and so ice shelves also do not contribute to sea level rise. So this is sort of just all a function of Archimedes' principle, which is that the weight of floating ice is compensated through the displacement of ocean water, which causes the level of the ocean to stay the same even if floating ice melts, right? And that's sort of the key difference between different types of ice on the Earth. Basically, whether it's floating or not determines whether it will contribute to sea level rise if it melts. And that's part of the activity that Jay was going to talk about. So I'm going to quickly just move through a few slides because we're going to talk about this a bit more in some of the webinars in the future when we talk about the Smart Sea Level Sensors project. But sea level is measured in a variety of ways. The old way sort of looks like this picture here. This is an old tide gauge station, which they usually sit on like a pier or a dock somewhere. There is a tube, or nowadays there is an ultrasonic sensor that points towards the surface of the ocean and measures sea level, perhaps over and takes an average over, let's say, an hour or some period of time, or it just takes continuous measurements of sea level and then later processes them. So this is most of the long-lived sea level data that we have is from these sorts of tide gauges. And actually in Northern Europe, there are tide gauge records that go back several hundred years that are fairly high quality. So the pros of this sort of measurement of sea level is that it's high accuracy and that in many places it's long-lived. The cons of this sort of measurement is that it's very expensive to maintain these tide gauge stations. They're relatively bulky, so usually there's one for a large region. There might not be more than, for example, in Georgia, there's only one tide gauge, long-lived tide gauge for the entire coast of Georgia, and that's actually largely the case, sort of up and down the coast, the southeast coast of the United States, and it's also one single point, which means that if any of the local effects that I've been talking about vary from one place to another, that point measurement might not be very representative of a large part of the coastline. Sort of a new way, and we'll talk about this more in a future webinar, but I just wanted to preview this. So the Smart Sea Level Sensor project is basically taking all the technology that went into these old tide gauge stations and miniaturizing it and connecting it to the internet so that you can build an entire tide gauge measurement device and pretty much put it anywhere where you can attach it to something solid for a few $100s. And so these are being used now through a project based out of Georgia Tech to pretty much blanket the city of Savannah and Chatham County with these sea level sensors and look at how very localized effects might cause you to have very different sea level changes or very different flooding conditions in different parts of the coastline. And at the very largest scale, the way that we measure sea level is using satellites. And so an example of this in the last 30 or so years is we've had these things called satellite altimeters, which basically shoot radar or some sort of laser or something at the surface of the ocean. They measure the amount of time that signal takes to get to the surface, bounce off the surface, and come back to the satellite. And based on very precise knowledge of their orbit, they can determine basically the position of the sea level at every location on the surface of the Earth, with some relatively good repeat time. So the benefits of this is, of course, that you have a measurement of sea level everywhere on the surface of the Earth, so it's not at a single point. The downsides of this is that that measurement is usually sort of fairly averaged over a fairly broad area called the swath of the satellite. And also the sampling is relatively infrequent. The satellite might only pass over that same area, once every few days or a few weeks. So just to wrap up, in thinking about future changes in sea level, there's a fairly large range. So this is another figure from the last IPCC report. And what this shows, the main thing to look at here are the gray boxes, and the gray boxes show basically the state-of-the-art predictions from about 5 to 10 years ago of what under different possible scenarios, so each box is a different scenario for future greenhouse gas emissions, how much sea level would rise from the 20th century to the end of the 21st century. And what you can see is that overall, there's quite a large range. So, these predictions are all vary over, some tens of centimeters of possible sea level rise. And actually, in the 10 years since this report was released, that range has only increased. And also that as you go from left to right, you have more and more greenhouse gas emissions that might be put into the atmosphere over the next 100 years. And so you can see that sea level rise goes like greenhouse gas emissions. As put more greenhouse gas into the atmosphere, the Earth's surface warms up more, and for the most part, the ocean thermally expands more quickly and glaciers melt more quickly. And so that was the state of the art about 10 years ago. And the next IPCC report, which is now just around the corner, will update this. And I think what people will find when they see that is that for the most part, the predictions have increased pretty much across the board for the amount of predicted sea level rise, and the range in those predictions has increased as well. With that sort of background completed, I'm going to turn things back over to Jema, who's going to wrap up in talking a bit about the curriculum.
The first activity we'll discuss is the JPL education, what's causing sea level rise, land ice versus sea ice activity, which is linked in our curriculum and is aligned with state and national standards. This is a hands-on activity that gives students the opportunity to investigate whether melting land ice or sea ice would have a greater impact on sea level rise, and it highlights the science and engineering practices that you see listed on the slide. Before conducting this investigation, students consider some background information, including that rising global average temperatures are causing land ice and sea ice to melt, and that those rising temperatures are being caused by climate change. And then they have to make a prediction where they predict the effect that melted sea ice and land ice would have on sea level rise. With enough materials, this is an activity that you could conduct in pairs of students, but if necessary, it's also possible to conduct this activity as a class demonstration. So first, I'll give you an overview of the original activity, and then I'll share how we tweaked it for our curriculum. So after students make their prediction and then create an explanation about which type of ice, if any, contributes more to sea level rise, they have to create a model of both the land ice and sea ice that they're going to test. Models are important concepts in science, and this is a great opportunity to ask students about what models are, that they're representations that can be used to test important aspects of the phenomenon under investigation, and why it's so important that we use models in this investigation, including that we don't have glaciers or access to sea ice in the classroom, and they're also not going to be traveling to any to test on their own. So to create their models, students are going to use two clear Ziploc type containers, clay, which will be used to represent land, a tray of ice cubes, water, which is going to represent the sea, a wet erase marker, and an optional hair dryer or heat lamp. Again, the students are going to use the two plastic containers, one which will be used to model sea ice and the other which will be used to model land ice, and they add the land by pressing equal amounts of clay into one side of each of the plastic containers. This is an important note. When students add the land, they should make a smooth, flat surface that represents land rising out of the ocean. They shouldn't create a lip at the edge of the land, which would prevent water from flowing off the land into the sea. It's time to add the water to their models and the ice. So in the land ice model, they first put a certain number of ice cubes on top of the clay to represent the land ice. In the sea ice model, they should put the exact same number of ice cubes at the bottom of the container. Next, they add the water. In the sea ice container, students should fill the container until the ice cubes start to float, but paying attention that the water is not higher than the land level. Then they should add approximately that same amount of water to the land ice container. At this point, with their models created, students should measure the height of the water either by using the ruler or by marking the side of the container with the wet erase marker. This is the starting position, and at regular time intervals, students are going to continue to measure or mark the height of the water until the ice in both containers has melted completely. To speed up the melting of the ice, depending on how much time you have in class, you can use either the hair dryers or heat lamps. Collecting the data, students are going to create line graphs visualizing how the water level changed over time in both containers. And then finally, the activity wraps up with reflection questions and a class discussion. Conducting this investigation, you have a great opportunity to stress to students the need to control several of the variables in the investigation, including the number of ice cubes that you use in both containers, the amount of clay, the shape of the land, the amount of water in the containers, and so on. This way, students can more accurately compare how the water level changed in both of the containers. A modified version of this investigation also highlights the same science and engineering practices, but is more inquiry-based and includes practice number 3, planning and carrying out investigations. Version of the activity, students are asked to design an experiment that will answer the question, does land ice or sea ice have a greater effect on sea level rise? The activity, more inquiry-based and less directive, gives students the opportunity to plan and carry out investigations and gives them more experience with understanding the importance of controlling variables. After finding out what materials they will have to work with, students are tasked with writing a procedure to investigate their question. From here, the activity follows the same path where students make a prediction, carry out their investigation, collect and analyze the data, and then reflect on it. And depending on your students' experiences with inquiry-based activities, conducting this version of the investigation may require more scaffolding, such as including a data table that they will fill in instead of having students create their own, and they might also need assistance with writing procedures. You can also give groups the opportunity to write and carry out their own investigations initially, and then share and compare the data as a class to see how reliable the data is overall. Depending on how consistent the class results were, you could then create a more uniform class procedure that all groups should follow that hopefully would result in more consistent data collected overall. There are many options with this activity, but hopefully through this activity, your students are going to learn more about what affects sea level rise, as well as some of the practices that scientists engage in as part of their work. Next webinar on Thursday, we're going to talk more about the phenomenon of coastal flooding in the Savannah and Tybee Island area. And we have a data analysis activity where students are going to analyze some historical data from Fort Pulaski and look at the high tide data in particular.
Great. Thank you very much.
Great. Thanks so much, Alex and Jema. I'm going to take over as presenter and share my screen. And seeing that it is already 12:35, we're not going to take questions, but if you guys do have any questions, please email communications@socorro.org. I'll make sure they get to Jema and Alex. And then as Jema said, register for the second webinar Thursday at noon Eastern. It is the introduction to the phenomenon of coastal flooding in the Savannah-Tybee area. And we look forward to seeing everybody on Thursday. Thanks so much, guys.